So as a super ambitious potential add-on, extra credit add-on to lab07, let's talk about the full wave bridge rectifier, which normally we do in class with a transformer, but we didn't really have it in a convenient form to send you to build at home. But we can go over it to some degree. I built a version of it over here on the EE board. And I used LEDs instead of diodes because the LEDs let you, red LEDs, the LEDs let you see what's going on. You can kind of see that each diode is active. And then I also built it in Circuit Lab. And Circuit Lab lets you kind of see what's going on in a way that is much less easy to do in real life. So let's go through that now. Yeah, so it is pretty tricky to think this through because on the signal source side here, and actually I think normally I just draw this like this, but let's think a little more about what's happening over here. Normally you have like the 120 volt. That's 100. By the way, when we say 120 volts, like for the US line voltage, the mains power. That's actually the root mean square, so the amplitude's more like 165 volts. Anyway, so you have we usually have a transformer, and in our classroom we have a transformer that brings it down by something like a factor of 8 or 10 with respect to the mains voltage, so it's a little safer to work with. So this is like 160 volts amplitude, and this is like, I think it's typically like 20 volts amplitude in our classroom, but it's going to be closer to 10 volts amplitude today with the EE board. But this is a floating voltage source, so it's not necessarily true that, say, the middle of this is grounded or that one side or the other is ground. I mean, it's not, you might think, well, maybe this side is always at ground, or you might think that maybe some point in between these two sides is always at ground. In general, in the transformer version that we use in class, neither one of those is true. The whole thing floats. And I'll show you in a moment why that is important for kind of maximizing the voltage that you get out of this. Okay, so I called these 2 points, I wasn't really sure what to call, I called them X and Y. Okay, so, right, so here's your X output and here's your Y output. And so what we know is that the voltage difference, X minus Y, is a sine wave, right? So we're going to say X minus Y is a sine with amplitude A. So I drew in yellow over here a kind of a representation of X minus Y as a function of time. So here's this yellow curve. So here X is higher, here Y is higher, here X is higher, here Y is higher. And what we're going to see, it's tricky to puzzle this through. What we're going to see is that the output peaks not 1 but 2 diode drops below A. And it takes a little bit of thinking to see why that's true. So let's consider 2 points in time. Let's first consider time point 1. Here, I'll call this T1. And this is where X minus Y is plus A. Okay, so at that instant, you know that X is A above Y. I guess that's just writing out what I said there. And, well, we're going to use this, so we want to use this output as sort of a useful output to power something. So let's just assume until I think we're not going to find a contradiction, so let's assume. So it seems like the output is probably going to be smaller than X, and it's going to be bigger than Y. And both of those are going to be true by more than a diode drop. So, so X is our highest point right now. So you say, okay, it makes sense that current can flow from X to the output. That's fine as long as the output stays lower than the voltage. As long as the output is lower than the amplitude by at least a diode drop, that seems to make sense. And then, if we look at this, see, this current could only flow if point X were at least a diode drop below ground. This point is grounded. So that doesn't make any sense. So there's no, oh, I guess I'm using X to mean two things. So this is the point X. This is meaning there's no current here. Okay. And G, here, let me make a different symbol, X. I don't know. Okay. That was unintended. So there we go. All right. So I'm using this for my capital letter X, which is different from the little x that I'm using to cross things off. Okay. Then we look down here, and you'd say this would only make sense if Y were above the output by at least a diode drop. And that's not true. So there's no current flowing here either. And now let's think about this. So does it make sense that ground is at least a diode drop above Y? Well, why couldn't that be true? And we do want the current somehow to flow back. You know, we need a complete circuit between output and ground. So it seems like this diode is on, which pulls point Y a diode drop below ground. Because we somehow need current to flow through the circuit between X and Y. So I guess the only other path is here, and that only works if this diode is on, and this diode can only be on if point Y is a diode drop below ground. So it seems like Y is one diode drop below ground. And then what does that imply? Well, actually, then you also see that the output is one diode drop below X. So when you think about that, here's ground. And then down here, we have Y, so this is a diode drop. And then up here, an amplitude A bigger. So this is X. And then a diode drop below that is our output. So you see, ground, down one diode drop, and then up A, and then down another diode drop to get to the output. Let's think about that. See, here's ground. And then from ground, we go down one diode drop to get to Y. And then from Y, we go up a whole amplitude to get to X, because we're at this part of the waveform. And then from X, we go down a diode drop to get to the output. So that tells us that at this instant, the output is the amplitude A minus 2 diode drops. That's sort of interesting. Okay, now let's consider what happens at this instant half a period later. So we're going to call this T2. Okay, so at T2, which is X minus Y is negative amplitude. Okay. So that means that Y is amplitude A above point X. Okay, so we'll think about that. So Y is amplitude A above this point X. Okay, seems plausible. So then we want Y is going to be above the output, so because we want current to flow. So this is our highest point in the circuit now, our highest voltage. So it makes sense that we'll have current flowing from Y to the output. So then I think then it makes sense we're going to say the output is one diode drop below Y. Okay. And then, so if the output is a diode drop below Y, now this point is going to be way below that, so it doesn't make sense that anything will flow this way, so there's nothing flowing there. And then over here, Y is very high. So if Y is our highest voltage, we're going to say it makes sense that it's way above ground. So there's no current flowing here because it would have to flow backwards across this diode. But X is now our lowest point, and so our lowest point can be a little bit below ground. So now we have current flowing from ground down to X. So then we have X is one diode drop below ground. So that's pretty tricky, right? So you say at one part of the wave, this diode pulls point Y down below ground by a diode drop. And then half a wave later, that this diode pulls point X down one diode drop below ground. So Y is a diode drop below ground at this part of the cycle, and then X is a diode drop below ground at this part of the cycle. So this thing is kind of being shifted up and down by the action of these diodes with respect to ground. So it's true that X minus Y obeys this nice sinusoidal pattern, but what X or Y individually doing with respect to ground is kind of tricky. And I guess so maybe the easiest way to see that tricky thing is to see it in Circuit Lab. Okay, so the net outcome of that is that our output waveform here, which is this sort of blue-gray curve, its amplitude is not one, but two diode drops below the amplitude of this X minus Y sine wave. And so it takes a little while to see that. And then you sort of see, right, these two diodes are on, then these two diodes are on. And these two diodes are on, these two diodes are on, then these two diodes are on, and these two diodes are on, and these two diodes are on. On, 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 on. And I think we can even see that with our blinking LEDs. That's kind of fun to see. Let me see if we can see that. Yeah, so I turned the frequency down to 1 hertz, but you can see, and the way I wired it up on the board is supposed to look like the circuits. You can kind of see dum dum doot 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 doot. Yeah, so you can see it's these two, 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 these two. Yeah. So you can see that pattern. See, that's the cool thing about doing it with the LEDs. So, okay, let's see what happens in Circuit Lab here. So I built the same circuit, and I'm using, see, notice that the signal generator here is floating. So I arranged the diodes the same way as I did on the board there. And here, you can even, I guess you can compare that way. So you see the arrangement of the LEDs or the diodes is the same as I drew on the board, and it turns out to be the same as the way I wired them up on the EE board. And then let's simulate and see what happens. And here, we're going to run a time domain simulation. And actually, there's one more expression I want to add, which is V plus minus V minus. So instead of saying X and Y, I said plus and minus on this one. Okay, let's see what happens there. I also graphed the currents through the diodes. So on the, actually this is kind of hard to read, isn't it? Let's see. All right, let me get rid of the, well, before, let's look at the currents and then I'll get rid of the currents. Okay, so if we go one diode at a time, here's the, actually before we do that, let's write down the numbering that I used here. Okay, so I called these 1, 2, 3, 4, I guess starting at the right side and going around counterclockwise. So then if we look at the current through diode 1, so it seems like 1 and 3 should be on at the same time, and that does seem to be true. 1 and 3 are on at the same time. And then we can look at number 2, and 2 is only on when 1 is not on. So it seems like 2 and 4 should be on at the same time. So there's 2, there's 4. So 2 and 4 are on at the same time, and 1 and 3 are on at the same time. So that makes sense. Okay, so that's kind of cool. So there's 1 and 3 are on together, and 2 and 4 are on together. 1, 2, 3, 4. Okay, cool. So now let me go back here and get rid of the currents. And then we can get a bigger picture of the voltages. Okay, so now we look at the voltages here, and we see who's who. Okay, first let's just look at V plus minus V minus. So there's our nice sine wave, and I made the amplitude of this sine wave be 5 volts so that it's not so big. I made it 5 volts is kind of small, but I made it that small so you can see the diode drops. Okay, so there's our nice 5. See, here's plus 5 volts. Here's minus 5 volts. We have our 5 volt amplitude sine wave. And then we can look at the output. And the output, you can see it kind of looks like the absolute value of the input, but then you say, what's the difference between the peak of, between our amplitude of the plus minus minus waveform and the peak of the output? It should be 2 diode drops below. So there's basically 5 volts versus 3.7. So 3.7 is, so that's like 2 times, right? So it's 2 times about 0.65. So it's 2 diode drops below. So that kind of makes sense. So basically this blue curve is 2 diode drops below the green curve. And then let's just look at the so-called plus input, which is what I was calling X. And that's kind of cool, because you see over here where plus minus minus, where our waveform is positive. So you can see the orange curve is in between the blue curve and the green curve. So you can see the orange curve is 1 diode drop below our amplitude, but then the output is a diode drop below that. Okay. And then meanwhile, you can say, well, what is the minus curve doing at that point? And the minus curve, this is kind of cool. The minus curve, you see, is sitting here at minus a diode drop. I don't know if you can read the numbers, but it says minus 0.63 volts, or minus 628 millivolts. So the minus curve is pulled down to minus a diode drop, and then that's why the orange curve, the plus curve, peaks at the amplitude minus a diode drop, and so therefore the output is the amplitude minus 2 diode drops. And then we'll go over and look at the situation here. Let me get rid of this. So you see this orange curve is up here. The orange curve peaks a diode drop below our amplitude. And now down at this part of the waveform, the orange curve is a diode drop below 0. And then when that happens, the brown curve is now a diode drop below the amplitude. So here's the amplitude up here. I guess you can't see that. The amplitude is going to be 5 volts, but then 5 volts minus a diode drop is this brown curve, and then a diode drop below that is the blue curve. And again, you see now the orange curve is pulled to, see here the brown curve is a diode drop below 0, and then the orange curve is a diode drop below 0, and the brown curve is a diode drop below 0, and then the orange curve is a diode drop below 0. So one diode drop comes from pulling whichever end is peaked lower. Well, actually, whichever end is lower. One diode drop comes from pulling the low end below ground through a diode. And then the other diode drop comes from the output being a diode drop below whichever one is higher. So that's kind of cool. Okay, so then if we get rid of these separate V plus and V minus things, then you see here's our output waveform. And it's basically, yeah, so its amplitude, its peak is basically its peak value is 2 diode drops below the amplitude of our kind of high minus low signal here. So then let's see what we get on the EE board. So first of all, what did I build here? So I'll point. So I tried to organize it to look like the Circuit Lab circuit. So in the top left corner, you have the diode I would call 3. The top right corner, you have the diode I would call 2. In the bottom right corner, you have the diode I would call 1. And then in the bottom left corner, you have the diode I would call 4. And again, I made them with red LEDs. Red has the lowest voltage drop of the visible LEDs. But they're visible. So, okay, so we have like about a 1.9 volt voltage drop instead of a 0.6 or 0.7 volt diode drop. Then now I don't have a transformer, so I'm using 2 channels of the waveform generator, and they're 180 degrees out of phase with each other. And I capacitively coupled both of them because I want the LEDs to be able to pull both of them down. So I have AWG output 1 going to one end of a big 10 microfarad capacitor, and then the other end of that big 10 microfarad capacitor is coming up to this point, which is the point where diodes 3 and 2 would meet. So I call that plus on the Circuit Lab circuit. And then channel 2 of the AWG goes to this big 10 microfarad capacitor. And the other end of that capacitor goes down to the point where diodes 1 and 4 meet on the Circuit Lab circuit diagram. And then the point where diodes 3 and 4 meet on the Circuit Lab diagram is over here, and that is this little black jumper to ground. So I have that point grounded. I also used this little black wire to connect the waveform generator ground to ground, but I don't think that makes any difference. I'm pretty sure this makes no, here I'll just unplug it. I think that makes no difference. All right. Then at the point where diodes 1 and 2 meet, that's basically my output. So I have a 1K resistor to ground. So the 1K resistor is my load. And then I'm using this green scope probe to observe the output. That's channel 1 of the scope. I actually have not tried observing like the points that we called plus and minus or X and Y with the scope probes, but I'm kind of tempted to do that now. So I actually think I might do that. But anyway, So there it is, and I have it running at 1 hertz so you can kind of see what's happening. But normally I was running it more like a kilohertz. Okay, then we can look and see what's happening in the Waveforms app. All right, so here's the Waveforms application. And I have 2 sine waves. Here I made them 1 hertz. We'll make them a little faster in a minute. But I made them 1 hertz so I could really see them. And then I made each one have an amplitude of 5 volts. And then one of them is 180 degrees away from the other. So this phase is 0. This phase is 180 degrees. Joe's came up with this idea. So we can credit Joe's with this idea. And then you want to do synchronize. Where's the synchronized? Somehow I told them, oh yeah, here they are, synchronized. Okay, so they're synchronized with each other. And then they're both enabled. I think to make sure they're synchronized, you want to stop all and then run all. Otherwise, it's possible for them to be out of sync. Okay, but we can go up to a higher, let's go up to a kilohertz. And we'll go up over here to a kilohertz. And then we'll go stop all and then run all. I think that resynchronizes everybody. And then we'll go over to scope. And now I don't quite understand why this doesn't come down quite to 0, but here's our V out signal. And then I've been meaning to add, so actually I have no idea what that's looking at right now, but let's add as a second scope channel. Let's look at the what I'm calling X or plus. So let's look at that. Okay, and I'm going to just put it on the same scale. So we want to go 2 volts per division. That's interesting. You see, it never quite gets pulled to ground through the diodes. That's kind of interesting. It's supposed to be pulled to like a diode drop below ground, and I think it doesn't quite work out. Oh, maybe it does. Maybe it does because the LED has a big drop. Okay, so I take it back. This may still be working. Okay, then we're going to add channel 3, and this is going to have no offset. And we're, offset 0. And we're going to do 2 volts per division. Hey, 2 volts per division, okay? And then I want to plug that in. Okay, so this gets plugged in above this other capacitor. Okay, that's kind of cool. And then the next thing I want to do, I think I want to crank up the amplitude a little bit so we can see see what happens, see if the diodes are really doing what I drew on the board. So go over to WaveGen. Let's go to 9 volts amplitude. And we'll go to 9 volts amplitude. We'll stop everybody, and then we'll restart everybody. Go back to the scope. And yeah, maybe it is working because, actually, okay, so I think maybe 2 volts per division isn't enough. Oh, no, I can just offset everybody. Let me offset everybody. Everybody's going to be offset by minus 4 volts. Let's try that. Maybe more. Minus 6 volts. Everybody's going to be offset by minus 6 volts. Minus 6 volts. Minus 6 volts. Oops, I need a minus sign here. Minus 6 volts. And yeah, I guess that's actually kind of neat. So the big amplitude is basically 18 volts, okay? Because we have the 2 sine waves, so so two 9-volt sine waves together makes an amplitude of 18 volts. Oh, we could also do a math thing here. Let's do a math thing, which is going to be, oh no. I'm going to try to set this up to be the difference of those two channels. Let me just pause while I do that. Yeah, so I got rid of the offset and I changed the scale. So let me just freeze this thing. And you see, so the red curve is the math function. It is like basically x minus y. So this is a sine wave with amplitude 18 volts. So this is 4 volts per division. So it goes from minus 20 up to plus 20. So this kind of makes sense. So because we have our two function generators together, 9 volts amplitude each. Here, let me see if we can see that. Here's 9 volts. Here's 9 volts. Phase of 0, phase of 180. So you see they're out of phase with each other. So we go over here, and we see the red curve is 18 volts amplitude. That's cool. And remember, with these LEDs, the diode drop is a little less than 2 volts. So now the blue curve here should be 1 diode drop below the red curve, and that makes sense. And then the yellow curve should be a diode drop below the blue curve, and that kind of makes sense. And then okay, so now we have the other half. So this is like 0.2 on our waveform instead of 0.1. So now the purple curve is a diode drop below the absolute value of the red curve. And the yellow curve is a diode drop below the purple curve. So that's all cool. The one thing that seems a little mysterious to me is why this yellow curve never gets down closer to 0. And yeah, I don't quite understand that, although come to think of it, maybe the problem is I didn't really, I thought I was being really clever with these big capacitors here, but come to think of it, one problem with these big capacitors is I don't really provide a DC path for current to flow. So anyway, so I'm a little confused what's happening with why the yellow curve doesn't get down all the way to 0. But it's still kind of neat. And then I guess the next step I was going to do, but I haven't done yet, was to add the filter capacitor. So maybe if I do that, I think it's going to be after class. I think I'm going to sign in now for class. So I might try adding the filter capacitor after class. So if you want to try this, one thing, you really want to be careful with the orientation of the LEDs. Or you could use diodes. If you do it with ordinary diodes, people tend, it's actually very common to blow out a bunch of diodes because it's very hard to orient these things just right. And then the diodes tend to blow in pairs, so it's kind of confusing. So it actually is a little easier to debug with the LEDs than with diodes because you can kind of see by eye right away if it's working. So you don't have to do this, but if you're like feeling really super duper ambitious, it's like I call it like a super duper extra credit option if you want to build this full wave bridge rectifier with the EE board using 4 LEDs, and you can use a pair of sine waves, 9 volts out of, 180 degrees out of phase. Joe's didn't use the blocking capacitors. So maybe if I have time after class, I might try taking them out and see what happens. And I'm also going to try putting the filter capacitor on. But now I'm out of time, so that'll happen later.